Hi everybody, I hope this video finds you well. In today's video, we're going to take a little look at the concept of level of significance, which we've been using for a while now, ever since we started studying hypothesis testing. We're going to talk a little bit about how level of significance relates to the type 1 and type 2 errors, and then we're going to look at a couple more examples of running the sort of new two-sample mean procedures that we've been discussing in the previous couple of videos. So we'll have a brief sort of discussion about level of significance, and then we'll jump into a couple examples just running the tests and talking a little bit more about error analysis. So first of all, level of significance and errors. So far, level of significance has been something that we've just been sort of given in each problem, but it turns out that level of significance has a direct relationship with the probability of making a type 1 and type 2 error. In fact, the alpha that you use in a particular hypothesis test is exactly equivalent to the probability, or at least the accepted probability, that you will make a type 1 error. What this really means is that if you decrease the alpha, you actually lower the chance of a type 1 error. If you make this alpha lower, then that's going to reduce the probability that you make a type 1 error. The problem, though, is that if you lower the chance of a type 1 error, you naturally raise the chance of a type 2 error. And that should sort of make sense. If you decide to make it harder on yourself to find evidence, that'll limit the chances that you commit a false positive error, but it will raise the chance that you miss a given effect. The opposite is true as well. If you increase your alpha, you naturally raise the chance of making a type 1 error. But as sort of a benefit, you lower the chance of a type 2 error. Mathematically, these two sort of sentences here basically tell you guys that the chance of making a type 1 error and the chance of making a type 2 error are inversely related. If you cause one to go up, the other will go down. Unfortunately, as we sort of discussed way back when we first introduced hypothesis testing, it's very hard to remove both types of errors, right? The harder you make it, the lower the chance of a type 1, the higher of a type 2, and vice versa. As a little sort of comment about this, most of the problems we've done so far have always used an alpha of 0.05, which is a very standard sort of statistical convention for significance levels. But you should keep in mind that a low alpha, like 0.01, is usually used when you're very worried about making a type 1 error, right? Because a very low alpha here, like we just said, that'll lower the chances of a type 1. While a higher alpha, something like 0.10, is usually used when you're worried about a type 2 error. So this again sort of is why we're spending a lot of time in this class talking about and always interpreting the different types of errors. You can really limit your exposure to one of the two types of errors. So it's important to know what each type of error would sort of mean, or what the impact of making that type of error would be, so that you know which type you want to try to avoid more of. Okay, so with that little discussion there, we're going to jump into a couple more examples of running these new procedures that we've learned, the matched pairs hypothesis test and the two-sample mean hypothesis test. But we'll also, at the end of each of these examples, spend a little bit more time talking about level of significance and error analysis. So let's get into those examples here. So for our first example here, we're going to suppose that you're studying if there's a possible gender pay gap at a large technology company. So you know that this company employs around 5,000 women and around 7,000 men. You want to study if the average salary for female employees is lower than for male employees. So to study this, you randomly select 41 female employees and 51 male employees from this company. You then record their salaries in thousands of dollars, and you get the following data. You find that for the female employees, they had an average salary of $63,000 with a standard deviation of $22,000, while the male employees had an average salary of $68,000 with a standard deviation of $29,000. So we're going to do two things with this. We're going to first carry out a hypothesis test at alpha equals 0.05, our standard level of significance, to test the claim that on average, female employees at this company make less money than male employees. Then we're going to sort of do a little bit of error analysis. We're going to say if you were concerned about missing a gender pay gap, i.e. missing that females make on average less than males at this company, should we have actually conducted our test at 0.01 or 0.10? So we'll see how to do this type of question in just a moment after we've gotten a little bit more practice just running these hypothesis tests. So let's jump right in and talk about how to approach A here. So we know that we're supposed to run a hypothesis test. We've got 3 different hypothesis tests to choose from: one sample mean, two sample mean, and matched pairs. Well, which one is this going to be? Well, our claim is about two separate populations. We're supposed to be comparing female employee salaries against male employees. That means that this is going to be a two-sample mean procedure. Remember, one sample mean is for when you have a single sample against a known average. We have two samples here, so it's not going to be a one sample mean, and it's not going to be matched pairs because we're not matching one person against themselves or one person against another directly. In fact, we can't do matching here because we took 41 females and 51 males, so matching would be impossible. So that tells us that this is going to be a two-sample mean hypothesis test. Okay, so let's go through and talk about how to run that then. So for the hypotheses, we know that for a two-sample mean hypothesis test, the hypotheses, well, at least the null, is always that the two populations are going to have the same average. In this case, we have females and males. Now remember, it doesn't matter which group you treat as the first one, as long as you stay consistent. Since this problem was sort of written with always saying female first and then male, we will use the female population as our first one. So we will say mu sub f, the average salary for females, should be the same as the average salary for males. That's our baseline assumption. What's our claim or our concern here for our alternate? Well, we're worried that females on average are making less. So our alternate is going to be mu sub f less than mu sub n. And that means that this, when we get to the p-value part, is going to be one-sided because we're using that less than there. Okay, let's go ahead and look at the conditions. First, we need both samples to be random and representative. Well, if we look back through here, it did say that we went ahead and we randomly selected 41 females and 51 males. So that's stated right in there. So we're all good with that. The second is we need to make sure that both sample sizes are less than 5% of the population sizes. Well, as always, right, remember sample size is guaranteed. You're going to know that. Population size may or may not. In this case, we know that one of our samples was 41 and the other one was 51. But we also know that the populations, the women and men who work in this company, we actually do have an estimate of that. 5,000 women and 7,000 men. So we can check this directly. N sub 1, which is going to be the sample size for the females, was 41. And we can check if that's less than 0.05 times the population for women, which was 5,000, which if you actually do that is 250. So 41 is definitely less than 250, so we're all good there. And then N2, which is the male sample size, that's 51. And then we have to check, is that less than 0.05 times the male population, which I believe we said was about 7,000. So if we check that, that's going to be 350, and 51 is less than 350, so we're all good there. For our third and final condition, we either need to check that the data is approximately normal, which is going to be hard because the information that we were given here is just the summary statistics, so we're not going to be able to do like a stem and leaf plot. Luckily, though, we have enough data that the central limit theorem assures us the sampling distribution will be approximately normal. So all we need to say here is that N1 is equal to 41, which is greater than or equal to 30, check. And N2 is 51, which is also greater than or equal to 30, so check. So all the conditions are met here. So we can move on to our test statistic. So for step 3, the test statistic here. Since we're working with quantitative information, we're doing that estimate of the population standard deviation with the sample standard deviation. So we'll need to use T. Our formula was x1 bar minus x2 bar over the square root of s1 squared over n1 plus s2 squared over n2. We'll make our little list, x1 bar, s1, and n1, and then x2 bar, s2, and n2. Now remember, from the way that we set this up, everything about sample 1 is going to reference the female sample since we put them first, and everything about sample 2 is going to reference the male sample since we put them second. So the average for females, it looked to be, they had an average value of 63,000 with a standard deviation of 22,000. It's okay to just carry that as 63. You don't need to put it as 63,000 since everything had a units of thousands of dollars. So their average was 63 and their standard deviation was 22, and we know the sample size for women was 41. For males, the average was 68, standard deviation was 29, and the sample size was 51. So there's our information there. Okay, let's go ahead and plug that stuff in. So if we do that, we should get T equals. Up top, we should have 63 minus 68, the two averages subtracted, and then divided by the square root of 22 squared divided by 41 plus 29 squared divided by 51. As always, good idea to just go ahead and do the top and bottom separately. So up top, we should see that we get minus 5. And down below, you should get 22 squared divided by 41 plus 29 squared divided by 51. Looks like you should get about 5.32. And then if you go ahead and you do your division, negative 5 divided by 5.32, looks like you should get about negative 0.94. Now, just as a quick side note, if when you were doing this on your own or you went back and you redid this, if you decided to put the male group first, then of course the alternate hypothesis would have been that mu sub m is greater than mu sub f. Down here, all of this stuff would have actually been for sample 1 and all of this stuff would have been for sample 2. And right here, the only difference is that instead of getting t equals negative 0.94, we would have gotten t equals 0.94. So you can see that the order really doesn't matter as long as you stay consistent with it. Okay, now we're ready to go on to step 4, our p-value. For our p-value, we know we'll be going on to table C, and we need to know our degrees of freedom. Remember that the degrees of freedom when you have a 2-sample procedure is you look at the 2 sample sizes, pick the smallest one, which in this case is 41, and still subtract 1. So this will be the minimum of 41 and 51 minus 1, which is going to be 40. So we have 40 degrees of freedom, and remember, since we have a negative t-value, we will be just using the absolute value, which is 0.94. So 40 degrees of freedom, and we're looking for 0.94. So if we've got our 40 degrees of freedom, and 0.94 would put us somewhere right about there. So 0.94 would end up right there. And we will follow that down to the one-sided peak because we have a one-sided hypothesis. So we will end up right there. So our p-value is somewhere between 0.20 and 0.15. Remember, the right side is always the low end. So we will reverse this when we write it down. So we will say that 0.15 is less than the p-value, is less than 0.20. So we know our p-value is located somewhere between 0.15 and 0.20, or if you prefer in percentages, it's somewhere between 15 and 20%. All right, we can go ahead and make our conclusion. So our conclusion is we compare that p-value against the alpha that was set, 0.05. How does this range compare? Well, the p-value is greater than 0.15, so it is certainly bigger than 0.05. So the p-value is greater than alpha of 0.05. That means we fail to reject HO. So we failed to throw out our baseline assumption. So we failed to find evidence. So we'd say no significant evidence for our claim. What was our claim? Well, you look at your alternate, that the average for females was less than the average for males. So no significant evidence that on average, female employees at this company make less money than male employees. So, in other words, we did not find significant evidence for a gender pay gap, at least at this company. Was there a bit of a difference in our sample? For sure, right? In our sample, women were only making $63,000 on average, while men were making $68,000. But given the amount of deviation that we saw and the relatively small sample sizes, we cannot conclude that what we saw in our sample was enough evidence to really believe that there was some gender pay gap overall in the company. Okay. Now let's go ahead, since this was just another quick example of running one of these hypothesis tests, we're doing something a little bit new and thinking about this part B here. So if this part B is saying basically, if you were really concerned about missing a gender pay gap, right, which obviously would be a major concern. This would be basically allowing a company that is underpaying people according to their gender and then letting them continue doing that. So you definitely don't want to miss if that is happening. Should we have actually run this test more at 0.01 or 0.10? In other words, should we have actually used a lower or higher alpha? Well, the way to sort of answer a question like this is to think about what type of error is missing a gender pay gap. Well, a type 1 error, remember, is a false positive. So a type 1 error would be where we think that there is a gender pay gap, but there really isn't. That's not really what this is describing. A type 2 error would be where we say, yeah, we don't have any evidence to throw this out, so we might as well stick with it, but we really should have thrown it out. In other words, this description right here is describing a type 2 error. So this right here, this is describing a type 2 error. If we're very concerned about a type 2 error, well, our initial discussion said that we should use a higher alpha. In other words, we should sort of loosen the standards of evidence. You can always think about that the lower the alpha, the more stringent your requirements are on your evidence. So if you're worried about a type 2 error, we should have retested at 0.10. So we should have done a retest at alpha equals 0.10. In other words, if this was really our concern, if we were very concerned about missing a possible gender pay gap, we really should have carried out our hypothesis test at alpha equals 0.10. Okay, so that's just giving you guys an example of running another 2-sample mean hypothesis test, as well as doing a little bit more analysis with errors. Let's go ahead and take a look at another quick example. All right, so for this example, we're going to change gears a little bit, and we're going to suppose that you're studying adult reading speeds. And you believe that adults can read faster if the subject matter that they are reading about interests them. So to study this, you find a random sample of 10 adults, and you have all of these adults first take a reading test on random material. Then you have them all take a reading test on a subject that they have indicated that they are interested in. And you get the following data. So here's our 10 subjects. Here's their words per minute, which is a way of measuring people's reading speeds when you had them read about random material. And here's their words per minute when you gave them material that they had indicated they were interested in. So you've got words per minute for when they read the random material, and you have words per minute for when they read their material they were interested in. Once again, we're going to do two things with this. We're going to get one more sort of round of practice of carrying out one of these new hypothesis tests. So we're going to carry out a hypothesis test at alpha equals 0.05 to test your claim that adults read faster on average when reading about a subject that interests them. And then B, we're going to do another one of these error analysis. We're going to say if you were worried about falsely claiming that adults read faster on average when reading about a subject that interests them, when in reality they do not, should you have tested at alpha equals 0.01 or 0.10? But let's start with the hypothesis test here. So, of course, as we sort of know, when we're starting to do one of these hypothesis tests, the first thing we have to do is figure out what sort of analysis we should do. Well, if we look at this here, we have these 10 subjects, and we tested them twice. Once with the random material and once with the interested material. And we're trying to see, was there a difference between what happened when they were interested versus what happened when it was just random? All of that indicates that this is going to be a matched pairs hypothesis test. So this is going to be a matched pairs hypothesis test. That means that we're not going to actually use this or this as our data. We need to calculate those differences. Remember, the differences you can do either way. You could do the random words per minute and then subtract the interested words per minute, or you could start with the interested words per minute and subtract the random words per minute. It's always easier if you sort of assure yourself of positive values. So if we look at this, right, the interested words per minute, 285, 319, 288, 284, so on, these are generally higher than these. So to make this a little easier on ourselves, we're going to calculate our differences as equal to the interested minus the random. So let's go ahead and calculate those up here. So we're going to actually be taking this guy and subtracting here. So the first one looks like we get a difference of 10, then of 12, then it looks like of 3, then it looks like 41, 34. We will get a negative 8. This person actually read a little bit slower when they were given the material they were interested in. Then 20, looks like 22, 24, and looks like 28. So there's our differences there. Notice that the 10 here indicates that this person read at 10 words per minute faster when they were looking at their interested material. This negative 8 represents that this person actually read 8 words per minute slower when looking at the interested material. Once again, it makes sense why we would be doing matched pairs here. Notice that everybody has pretty different reading speeds. Some people are in the sort of mid to high 200s. This person is sort of in the mid to low 200s. There's people in the 300s, so on. We don't care about what their natural reading speed is. We care if it went up when they were given interested material. And you can see that even though some of these people might have been still having relatively lower reading speeds, for example, this person was still only in the high 200s, they had a massive increase. So we care more about these differences than we do their individual scores. And again, that's the whole point of a matched pairs analysis. All right, let's get into actually running this test then. So first thing we need to do is we need to look at our hypotheses. So we have our HO and HA. Remember, when you're doing a matched pairs hypothesis test, you change your notation to D to represent those differences. So we've got two things that we need to do here. We need to fill in this null value and our inequality here. Well, let's go back and read our claim here. We're trying to claim that adults read faster on average about a subject that interests them. Notice it doesn't say how much faster. So there's not really a null value being given. So it is not immediately clear what value we should put in here. But imagine you sort of think about it from this way. If we didn't really know any better, if we didn't think that people would read faster here, then we would expect that when they read here and when they read here, it's going to be the same, right? If they're just reading, if nothing has changed, their reading speed should be the same. Well, that means that that difference should be 0. That would be our baseline assumption. In other words, we're sort of in this special case that happens with matched pairs, that if no size of the difference is given, we sort of make an assumption that the difference should be 0. So our null value is going to be 0 and 0. And since we think that they might, our claim is that they will read faster over here, we think that those differences should be greater than 0. That is our claim. So this is sort of a special case here, something you guys should just watch out for. If you're ever seeing an example where you're asked to run a matched pairs analysis, but no null value is given, then you have to realize that that null is actually going to be 0. Okay. Notice also, since we are doing greater than 0, because they're supposed to read faster on average, well, this means that this guy here is going to be a one-sided test. Okay, let's get in then to the conditions. So for the conditions here, first one, we needed random and representative, and that was stated. How do we know that that was stated? Well, it says right in here that we gathered a random sample of 10 adults. So we've got that. Second, we need to make sure that our sample size is less than 5% of the population size. Well, our sample size is very small. In this case, we only looked at 10 adults. And of course, our population is all adults, so there's no worries here. We can just put lots of adults, since we have no information about the overall population size. The third and final one, we've gotten away a lot of times by just saying that our sample size is greater than size 30. That's not going to work here because we only have 10 subjects. So we're going to need to actually look at the data. Specifically, we're going to need to look at these differences. So we need to check, are the differences approximately normal? So we can do a nice stem and leaf plot here. Our stems will be things like 0 and 1 and 2 and 3 and 4. But we will have one weird thing. We'll actually have to include a -0 to separate the -1, 8 from that positive 3. So our stem and leaf plot here should look like -0, 0, 1, 2, 3, and 4. For that -0, we had that -8. For the positive 0, we had 3. For the 1, we had 10 and 12. So we had 10 and 12 there. Then for the 20s, we had 20, 22, 24, and 28. Then for the 30s, we had 34. And then for the 40s, we had 41. Again, what are we looking for here? Well, we're hoping it looks roughly normal, which we can sort of see. There seems to be sort of a peak there and then tails to both sides. But what we really care about is that there were no strong skew. That's very important. But the most important thing is that there are no outliers here, right? None of these sort of differences were super far away from the others, so there's no outliers. All right, let's go ahead then and get our test statistic. Our test statistic here is going to be T equals D bar minus D over SD over root N. Though do keep in mind that this test statistic sort of calculation here, this is just like the one sample mean, except that everything here is reminding you that it's about the differences. We've got 4 things that we need to know here: D bar, D, SD, and N. Some of these we've already used. D was supposed to be 0, so we have D equals 0. And we know that the N, we've mentioned that a couple times, it's 10. Now we need to find the average and the standard deviation of those differences. So now it's time to grab that stuff, right? Grab all these differences and pop these into L1 and use your 1var stat. So if you have a calculator, right, you can go ahead and do this as I type this in as well. So type in those differences: 10, 12, 3, 41, 34, -8, 20, 22, 24, and 28. Do make sure that when you guys go ahead and you type in that -8, you use the negative key, which is usually located down at the bottom of the number area, like near the 3 and usually the decimal point, and not the subtraction key, which is located by the plus and the times sign. So make sure you use the negative key near the 3 and the decimal point to type that in. Once you do that, you can go ahead and use stat calc and your 1var stats, and you can go ahead and get your average and your standard deviation. So when we do that, you should get an average of 18.6. So on average, the people with the interested subject material were reading 18.6 words per minute faster. And you should get a standard deviation. Make sure you grab the sample one of 14.7. So we can pop all that stuff in there. We should get T is 18.6 minus the null, which is 0, divided by 14.7 divided by the square root of 10. We can go ahead and calculate that. As always, go ahead and do the top first, 18.6, and the bottom separately. So we got to take 14.7 and divide by square root of 10. Looks like we should get 4.65 there. Then go ahead and do that actual division, 18.6 divided by 4.65. And if you do that, you should get 4.00 about. Okay, so there we go. We got a t-value of about 4. Now we're ready to go ahead and grab our p-value. So our p-value here, we will need to use table C, and we'll need to know that our degrees of freedom in this case is going to be 10 minus 1, which is 9. Remember, that's because our sample size was 10. We subtract 1, giving our 9 degrees of freedom. Remember, we will also be using our one-sided p-value. So we've got a t-value of 4, degrees of freedom equal to 9. So let's go ahead and look at that. So with our 9 degrees of freedom right there, our t-value of 4 puts us somewhere over here. So we get our 4 right there, in between that 3.690 and our 4.297. We'll follow that down. We'll have to zoom out just a little bit. Follow that down to the one-sided p section, and we should find ourselves right there. So the low end is 0.001, and the high end is 0.0025. So we can go ahead and record that. Our p-value is somewhere between 0.001 and no larger than 0.0025. All right, we're now ready to sort of squeeze in our conclusion. I'll put this a little bit over here so we have a little bit more room. Our conclusion, well, if we take this p-value and we compare it against the alpha that was given, 0.05, how does this p-value compare against alpha 0.05? Well, this p-value is coming in less than 0.0025, so it is certainly less than 0.05. That means we will be rejecting HO in this case. Now, generally, I find that rejecting HO is the easier conclusion. That means we're throwing out this and going with that the difference is greater than 0. If the difference is greater than 0, that means that the interested is higher than the random. So we would be saying significant evidence that on average, reading speed is higher when interested. So in other words, we're basically saying that we do have significant evidence that we believe that on average, your reading speed will be increased if you are interested in the material. Okay, so there we go. There's another example of one of sort of our newer hypothesis tests, the matched pairs hypothesis test. Remember that pretty much you guys should be able to identify a matched pairs hypothesis test almost just visually. When you see data that's presented like this, where you sort of know how a group of subjects or a sample was sort of tested twice. Remember we said, matched pairs often is test 1, test 2, or before and after. This time it's that same thing, except that instead of calling it test 1 and test 2, test 1 happened to be random material and test 2 happened to be material they were interested in. But visually, matched pairs data should really jump out to you. All right, let's quickly talk about part B here. So if you were worried about falsely claiming that adults read faster on average when reading about a subject that interests them, when in reality they do not, well, how would we decide that they read faster on average? Well, to decide that they read faster on average, that sounds like we'd be throwing out that there is no difference and going with that interested really is greater than random on average. Well, that means that this is sort of describing a false positive, where we think something is going on, but it's really not. So this is describing a type 1 error. Well, if your concern is about a type 1 error, you need to set a lower alpha to make it harder to find evidence. So we would use an alpha of 0.01 if we were going to retest, because we'd want to make it harder on ourselves because we're very concerned about making a type 1 error. So in this video, we've taken a look at a couple more examples of running these new procedures, the 2-sample mean procedure and the matched pairs, and we talked a little bit more about understanding type 1 and type 2 errors, and specifically how they relate to significance level. In our next video, which will be the last one on this sort of section, we'll talk just a little bit more about the identification process of making sure we're comfortable with 1 sample versus 2 sample versus matched pairs, and we'll also talk a little bit more about confidence intervals.